In electrical systems, zero plays a crucial role, primarily in the context of grounding and neutral conductors. Grounding is a fundamental safety measure designed to protect individuals from electrical shock and to safeguard equipment from damage due to fault currents. The neutral conductor, often referred to as the grounded conductor, provides a return path for current in a typical electrical circuit. Understanding the relationship between ground and neutral is essential for ensuring a safe and properly functioning electrical system. Let's start by defining some key terms. Ground, in electrical terms, refers to a connection to the earth. This connection provides a low impedance path for fault currents to return to the source, which allows protective devices, such as circuit breakers or fuses, to trip and to energize the circuit. This rapid energization minimizes the duration of a potential shock hazard and reduces the risk of fire. A neutral conductor is the conductor that carries current back to the source in a single-phase alternating current, also known as AC system. The neutral is typically connected to ground at the service entrance, which is where the power enters the building. This connection creates a common reference point of 0 volts. The purpose of grounding is to provide a safe path for fault currents. A fault current occurs when a live conductor comes into contact with a grounded surface, such as the metal enclosure of an appliance or a piece of equipment. Without a proper grounding system, this fault current could energize the enclosure, creating a shock hazard for anyone who touches it. While a grounding system is in place, the fault current flows through the grounding conductor back to the source. This high current causes the circuit breaker or fuse to trip, immediately cutting off power to the circuit and eliminating the shock hazard. The National Electrical Code, also known as NEC, provides detailed requirements for grounding electrical systems. These requirements specify the size and type of grounding conductors, the methods for connecting grounding electrodes, and the bonding requirements for metallic components. Bonding refers to the practice of connecting all metallic parts of an electrical system together to create a continuous electrical path. This ensures that all metal components are at the same potential, preventing voltage differences that could cause shock hazards. The NEC requires that the neutral conductor be grounded at the service entrance. This is typically accomplished by connecting the neutral conductor to a grounding electrode system, which may consist of ground rods, ground plates, or the metal water pipe of the building. The grounding electrode system provides a connection to the earth, ensuring that the neutral conductor is at or near 0 volts relative to ground. It is very important to note that the neutral should only be grounded at one point, which is at the service entrance. Grounding the neutral at multiple points can create unwanted circulating currents and increase the risk of electrical noise. There is a critical difference between the neutral conductor and the grounding conductor, also known as the equipment grounding conductor, even though both are ultimately connected to ground. The neutral conductor carries current under normal operating conditions, providing the return path for the flow of current in the circuit. The grounding conductor, on the other hand, only carries current during a fault condition. Its sole purpose is to provide a low impedance path for fault currents to return to the source. The grounding conductor is typically a green or bare wire, and it is connected to the metal enclosures of equipment and appliances. The NEC specifies different types of grounding conductors, including equipment grounding conductors, bonding jumpers, and grounding electrode conductors. Equipment grounding conductors are used to connect the metal enclosures of equipment to the grounding system. Bonding jumpers are used to connect different metal parts of an electrical system together, such as metal conduits, metal enclosures, and metal water pipes. Grounding electrode conductors are used to connect the grounding electrode system to the neutral conductor at the service entrance. One important aspect of grounding is the concept of impedance. Impedance is the total opposition to current flow in an AC circuit, and it includes both resistance and reactance. A low impedance grounding path is essential for ensuring that fault currents can flow quickly and easily back to the source. This allows the protective devices to trip quickly and minimize the duration of a potential shock hazard. The NEC specifies the maximum impedance values for grounding conductors and grounding electrode systems. These impedance values are designed to ensure that the grounding system is effective in clearing fault currents. Another important consideration is the size of the grounding conductors. The NEC specifies the minimum size of grounding conductors based on the size of the overcurrent protection device protecting the circuit. For example, if a circuit is protected by a 20 amp circuit breaker, the minimum size of the equipment grounding conductor is typically 12 American wire gauge, also known as AWG copper. If the circuit is protected by a 60 amp circuit breaker, the minimum size of the equipment grounding conductor is typically 10 AWG copper. The NEC provides detailed tables that specify the minimum size of grounding conductors for different sizes of overcurrent protection devices. In addition to grounding conductors, bonding is also an important part of the grounding system. Bonding refers to the practice of connecting all metallic parts of an electrical system together to create a continuous electrical path. This ensures that all metal components are at the same potential, preventing voltage differences that could cause shock hazards. The NEC requires that all metal enclosures, metal conduits, metal water pipes, and other metal parts of an electrical system be bonded together. This bonding is typically accomplished by using bonding jumpers, which are short lengths of wire that connect the different metal components together. The grounding electrode system is the connection to the earth. The NEC specifies different types of grounding electrodes that can be used, including ground rods, ground plates, and the metal water pipe of the building. Ground rods are typically 8 feet long and are driven into the ground. Ground plates are typically made of copper or galvanized steel and are buried in the ground. The metal water pipe of the building can also be used as a grounding electrode, provided that it is in direct contact with the earth for at least 10 feet. The NEC specifies the minimum number and type of grounding electrodes that are required for different types of electrical systems. When installing a grounding system, it is important to follow the NEC requirements carefully. This includes using the correct size and type of grounding conductors, properly connecting the grounding electrodes, and ensuring that all metal components are bonded together. It is also important to inspect the grounding system regularly to ensure that it is in good condition and that all connections are tight. A loose or corroded grounding connection can significantly reduce the effectiveness of the grounding system and increase the risk of electrical shock. In addition to grounding, ground fault circuit interrupters, also known as GFCIs, provide additional protection against electrical shock. A GFCI is a device that monitors the current flow in a circuit and detects any imbalance between the hot and neutral conductors. If a GFCI detects an imbalance, it quickly trips the circuit, cutting off power to the circuit and preventing the electrical shock. GFCIs are typically installed in areas where there is a high risk of electrical shock, such as bathrooms, kitchens, and outdoor locations. Arc fault circuit interrupters, also known as SIs, provide protection against arc faults, which are dangerous electrical faults that can cause fires. An arc fault occurs when electricity jumps between two conductors, creating a high-temperature arc. SIs are designed to detect these arc faults and trip the circuit, preventing a fire. The NEC requires that SIs be installed in many areas of the home, including bedrooms, living rooms, and dining rooms. Proper grounding is essential for electrical safety. It provides a safe path for fault currents, minimizes the duration of potential shock hazards, and reduces the risk of fire. By understanding the principles of grounding and following the NEC requirements, one can ensure that their electrical system is safe and properly functioning. The neutral conductor, grounded at the service entrance, serves as the return path for normal current flow, while the equipment grounding conductor provides a low impedance path for fault currents. Bonding ensures that all metallic parts are at the same potential, preventing voltage differences. GFCIs and SIs provide additional layers of protection against electrical shock and arc faults. The 0-volt reference provided by the grounding system is critical for the proper operation of many electronic devices. Many electronic devices rely on a stable ground reference to function correctly. Voltage fluctuations on the ground can cause these devices to malfunction or even be damaged. A properly grounded electrical system helps to minimize these voltage fluctuations and ensure that electronic devices operate reliably. In summary, zero in electrical systems is intimately tied to the grounding and neutral conductors. Grounding protects against electrical shock by providing a low impedance path for fault currents. The neutral conductor, grounded at the service entrance, provides the return path for current in a normal circuit. Bonding ensures that all metallic parts are at the same potential, and GFCIs and FCIs provide additional layers of protection. Understanding these concepts is essential for ensuring a safe and properly functioning electrical system. The 0-volt reference provided by the grounding system is also crucial for the proper operation of many electronic devices. Grounding is a critical aspect of electrical safety and should not be overlooked. Regular inspection and maintenance of the grounding system are essential to ensure its continued effectiveness. Always consult with a qualified electrician when working on electrical systems to ensure that all work is performed safely and in accordance with the NEC.